So just keep a note here that there will be more questions on the next slide. There we've got there, and there we've got there. Okay, so it says the flow diagram below shows how compound A can be used as a starting reactant to prepare two different compounds. 1, 2, and 3 represent organic reactions. Right, so the first question says, is compound A primary, secondary, or tertiary haloalkane? So please always draw it out, okay? So I just start on the left-hand side, and I don't look at any of that, I just start piece by piece. So the first part is a CH3. Okay, CH3. There we go. Now that part's done. Then there's a carbon. Okay, carbon. Then there's a CH3. Now some students are going to be confused. They're going to say, does that mean it's part of the chain, or does it mean it's a branch? Well, it cannot be a chain because you can't put a CH3. That would only be a CH2. Because if you put the other hydrogen, well, then you've ended your whole chain. So rather put it as a branch. So you can either go up or down. So I'm going to go down like that. So now the CH3 is done. Then there's a Br, okay? That can't be there. You never get a Br somewhere in the middle. Like, how weird is that? So it has to go there. Then there's a CH2. Okay, that makes sense. A carbon with two hydrogens. And then a CH3. There we go. And then obviously all of these are hydrogens, right? There we go. So just like with primary alcohols, secondary alcohols, and tertiary, we can do the same with haloalkane. So what you do is you go find the halogen. So there's your halogen, okay? Then I want you to look at the carbon that is directly touching that one. So there it is there. Now I want you to see how many carbons are directly connected to this one. Well, there's one over here. You can't count this one. That's not directly touching this one, okay? Then there's one over here, and then there's one over here. So that's 3. So that would be tertiary. And it says give a reason for your answer. So you could say the halogen is bonded to a carbon which is itself bonded to 3 other carbons. Moving on to this one, it says consider reaction number 1, and it says besides heat, write down the other reaction condition. Okay, so we need to know, I should have actually kept compound A. So let's quickly just draw out compound A once more. We had a CH3 like that, and then we had a CH3 down here. We had a Br, and then we had CH2 and CH3. Okay, and I'll go put all the hydrogens. And now they're telling us that that is going to be converted into alkene. Alkene. How do I know that that's an alkene? Because I know that alkenes have a general formula that is CnH2n. So that means that the hydrogen always has double the carbon, and 5 and 10. So it's definitely going to be an alkene. So what we'll probably have is we're going to have our normal 4 carbons, which we still have here in this main chain, and we would never lose that branch over there, so that's still going to stay. And so there's the 5 carbons. Now, we got to try to figure out where the double bond is. I don't even know if we're going to need to know that for this. They are going to ask us for the structural formulas later on. Okay, so let's just do it anyways. Excellent. So we got to try to figure out where the double bond is going to go, because alkenes have a double bond. So check this out. There's no Br over here. So we're definitely going to lose this Br. So we can, let's go fill in all the, we don't know if we're going to lose a hydrogen. Okay, so we know that that's going to be lost, this Br. Okay, that's gone. Then, to be able to make a double bond, we need to lose something on either this carbon over here or this carbon over here, so that we could then put a double bond either there or there. But you can't just choose whichever you feel like. You got to use the organic chemistry rules, which is that whole riddle that we sometimes say with the richer get richer and the poorer get poorer. So richer get richer, and then the poorer get poorer. And remember, when we're doing that, we're talking about hydrogen. Okay, now this is going to be an elimination reaction because you're taking things away. You're taking things away from this molecule. So we're not going to look at the richer get richer part. That's only when you are busy with addition. So let's make a little note here. That's only when we are doing addition. What we're doing is the poorer get poorer. And that is where you do elimination. Okay, so the way it works is you don't look at this carbon here because that carbon already lost the bromine. So you look at the carbons next to that one. So it's going to be this one, or technically you could even look at that carbon as well because it is touching it. So you then look at those carbons, those 3 carbons, and you look and see which one is the poorest in hydrogen. So we know that this carbon here has 3. It's got 1, 2, 3 hydrogens. Okay. Then this carbon over here also has 3 hydrogens. You see them there? And then this carbon over here only has 2. So that means that this carbon is the poorest, and the riddle tells us that the poorest one gets even poorer. That means that we are going to lose one of these hydrogens. If you wanted to lose the one at the bottom, that's okay. They don't really, in the exams, they don't mind about that. It doesn't matter at all. So let's eliminate this hydrogen. So that means we've lost this thing over here. And then everything else will stay the same. So let's go draw in everything else, and then you'll see how the double bond fits in. Okay, now you see we have a bit of a problem because we've lost the Br and we've lost the hydrogen. But now, if you look at this carbon over here, it only has 1, 2, 3 bonds around it. If you look at this carbon over here, it has 1, 2, 3 bonds around it. And that is where we can now use the double bond to make sure that we have 4 bonds around this carbon and 4 bonds around that carbon. So that is the elimination reaction over there. Now, I know that that's not, we didn't need to do that for this question, but I wanted us to have a very good visualization of what exactly is going on here. So it says, besides heat, write down the other reaction condition needed. So if you've ever looked at my diagrams where I show you all the different organic reactions, we always have at the top here, we've got alkanes, and then we've got an arrow going to haloalkane, for example, and then we've got arrows going back to alkene, right? And obviously there's a whole lot more reactions. There's plenty of reactions, but there's this one, and then we also know that there's one that goes down to alcohols. And we can also go from alcohol to haloalkane. We can go from this way. We can go this way. We can go... I've showed you this diagram before where we've got all these different reactions. But what's important is the one we're busy with now, which is when you have a haloalkane, okay, which is here, and then you end up with an alkene. So it's this reaction over here. And so I've spoken to you guys about this at length before, where with haloalkanes, you need to be careful. Because haloalkanes, they've got 2 different reactions they can do. You can go from a haloalkane to an alkene, but you can also go from a haloalkane to an alcohol. And this is the one where both of these reactions, they make use of, so let's write out the conditions here. Both of those reactions make use of a strong base, such as sodium hydroxide or typically potassium hydroxide, one of those. But if you use a concentrated strong base, then it does one type of reaction. And if you use a dilute, then it does the other type of reaction. And you need to know this. So I've spoken to you guys about this before. If you go from a haloalkane to an alkene, we said that is elimination. And we've said before that elimination is very aggressive, right? It's a very aggressive kind of thing. Like if someone says, hey bro, you are eliminated. Like that sounds pretty violent if you ask me. Whereas if someone says, hey bro, you need to come off the field so that I can come back on, so that I can come onto the field. So I need to substitute. We need to make a substitution. That's not so bad, okay? But when someone says, hey bro, you out, you eliminated, that's aggressive. So what word is more aggressive? The word dilute or concentrated. So it's definitely concentrated. Concentrated is a more aggressive kind of thing. Dilute is like, hey bro, I made you some Oros, but I decided not to add that much Oros, so it's a bit dilute. Like, that's a bit lame, it's boring. But if someone's like, hey bro, I decided to give you half a glass of Oros and half a glass of water, it's concentrated, it's aggression. I don't know, like, I think you can make any word sound aggressive by the way you say it. So yeah, I don't know. But the word concentrated must make you remember elimination. Elimination, aggressive, yeah. So I don't know how you want to remember that, but you just got to remember that when they use concentrated, that means elimination. Okay, so concentrated, elimination. Dilute, substitution. Got it? So it says here, besides heat, write down the other condition needed. You would need to use a concentrated, strong. Those are not the same things, right? This is not the same as this. They're two different things. So we're using a strong base. A strong base is just a base that loves to dissociate, such as potassium hydroxide or sodium hydroxide. But being concentrated is another, it's not the same as being strong. Okay, you can get something that's strong and dilute as well. And then because they didn't tell us what base we're using, I did check on the memo and they will not mark you incorrect if you put something like concentrated NaOH or concentrated KOH. You can also do that. Okay, but you must use the word concentrated. That's a non-negotiable. Right, so it says besides, okay, so we've done that. 4.2.2. Write down the type of reaction that takes place. Well, that is elimination. You could also call it like you could call it dehydro, because we're getting rid of a hydrogen and we're getting rid of a halogen. So you could call it dehydrohalogenation. Let me write that better for you guys quickly. Dehydrohalogenation. And then the last question for 5 marks, using structural formula, so these are structural formula, write down a balanced equation. Okay, so this is not going to be good enough. We actually need to go add a few more things. So these drawings that we do have, we are going to keep those, but we need to add a few more things here. So now that we're going to go write down the reaction, I'm not sure if you've watched that video where, it was one of my reaction videos where we spoke about a haloalkane going to an alkene, but there are two methods that different textbooks and different teachers in South Africa use. We've got method 1 and we've got method 2. You remember that video that I've done before with you guys where we've looked at that. Okay, so I will do both. On the memo they only do the one, but both of them are valid, and I'll show you how to do it for both techniques, okay? So for the first one, I will treat the base as a reactant, and then for the second one, I will treat the base as almost like a catalyst. Okay, so let's do method number 1. So this will be number 1. So we're going to treat the base as a reactant. So that means you're actually going to say plus. Now, let's use NaOH. You could have chosen KOH, but I'm just going to go with NaOH. Okay, put an arrow. Now, here's your reactant. You've got this. And then you're going to have NaBr. I will explain now where that comes from. And then H2O as your other product. So, the Na combines with the Br that came off, and they become sodium bromide. And then the H that we gave away, remember that H, and that OH, they combine to become water. Okay, so that is how option number 1 would look. Now I'm going to do option number 2. Okay, so I'm gonna erase all of this now, and I'm going to do this, and I'm going to do this. Now with option number 2, we don't say plus because it's not a reaction with the base. The base is like a catalyst. So what your teacher might do is they just write it at the top here. So maybe NaOH. Okay, now what happens, oh, and then we've got that. Now what happens is that your product is going to be this over here plus HBr. Let me explain. So the NaOH is now not getting involved in the reaction. So we don't see any Na and OH over here, and we don't see any Na and OH in the reaction over here. So all that happens now is that the H and the Br that were eliminated, they just combine to become that over there. Okay, if you're unsure about what I've just done, then go look at that video in the playlists on the reactions. It's where we have a haloalkane turning into an alkene, and in that video I do share 2 different methods that are used in by teachers in South Africa. This question says, consider reaction number 2. Okay, so this is reaction number 2, where we're taking compound B. So let's immediately go draw compound B before we even look further. We looked at compound B in the previous question, so we should still remember all about that. Or something to do. Let me just go back here. It was this one, remember? Okay. There. Boom. Boom. Okay, so that's what we had, and then they said that we are going to convert that into this. Now, if you look carefully here, there's 5 carbons and 5 carbons. But then there's 10 hydrogens, and now there's 12 hydrogens. That means that they've added 2 hydrogens, and then here there's no oxygen, but here there's 1 oxygen. So they've added water. So what will happen if you take a alkene and you add water to it? Well, if you think of water as H connected to an OH, we know that the hydrogen will end up going here or here, and then the OH will go to the other one. So if the hydrogen ends up going here, then the OH would go there, or vice versa. We'll have to figure that out. So we're going to develop an alcohol as a product. For those of you that have studied my reaction diagrams before, then you should remember we've got alkanes over there, we've got haloalkanes over there, alkenes, and then alcohols. And then we've got, so what we have here is we've got an alkene that is being converted into a alcohol. Okay, and so to try figure out what the major product is going to be, we need to go back to richer get richer, and the poorer get poorer. And remember, we're talking about hydrogen. So, because we need to try figure out where's this hydrogen going to go, and where's this OH going to go. So when we are doing an addition reaction, where you're adding something onto another molecule, then we only look at this part of the riddle. Okay, we don't look at the poorer get poorer. That's only with elimination, like we looked at in the previous part of this question. So what we do is what happens is that this double bond is going to be broken up into a single bond, and then you're going to have attachment points now over there and over there. Let me explain that. Because here when you have a double bond, you can see that in this carbon there's 1, 2, 3, 4 attachments or bonds, and then here you've got 1, 2, 3, 4 around that carbon. But now what happens is that if you break that double bond, then what that allows is extra 2 points over there. But what you'll notice is that each carbon is still surrounded by 4. See that? And so that's what happens over there. Now we got to try to figure out this hydrogen. So it says that the richer get even richer. So if you look at this carbon, and if you look at this carbon, how many hydrogens did they have at that moment? Well, this one over here has 1 hydrogen. There it is. This one has absolutely 0 hydrogens. Can you see that? There's no hydrogens. So who's the richest in hydrogen? Well, this one's the richest. And what does the riddle say? The richest one gets even richer. And so this hydrogen's going to end up going there, and then the OH would end up going over there. So let's quickly draw that in. So your product would then have the hydrogen over there and then the OH over there. If you did it the other way, that is wrong. That is called the minor product, but they would like us to do the major product. Okay. So it says write down the structural formula. That is the structural formula. And you must remember that if your diagram is a bit not backwards, but different to mine, like if you have the OH on this one and you've got this part over here, that's fine. That's absolutely fine. Okay. This question says, name or formula of the inorganic. Inorganic is a molecule, something that doesn't have carbon. Okay, so that's going to be the water. The water is what we need. Remember, I just told you we're going to add water. Okay, so you could either say H2O or you could say water. Then it says, what is the type of addition? Well, with the types of addition, we've got halogenation, hydrohalogenation, that's just completely wrong. So we've got hydrohalogenation, halogenation, hydration, hydrogenation. So here we are adding water. So that one is called hydration. Just like if you drink water, you are hydrating. Here's the last part of this question. So it says, consider reaction number 3. It says, write down the type of reaction. So let's see what we have here. We've got a haloalkane. I don't care what this is. I just want to know what kind of molecule. Like, I don't need to know exactly what it is. I just want to know the homologous group. And then here we've got an alcohol. Okay. So on our reaction diagram, this would be alkanes. Come on. Alkanes. Alkenes, and then haloalkanes, alcohols. And so what we have is we have the haloalkane turning into an alcohol. Whereas in the previous part of this question, when we were looking at, I think it was this one over here, this is the one where we had a haloalkane going to an alkene, where we had to use a concentrated strong base. Now we are going from a haloalkane again, but now we're going to an alcohol. And if you were listening carefully, I reminded you at that time where we said that a haloalkane can have two possibilities. It can go to an alkene or it can go to an alcohol. In both of those, you have to use a strong base. Strong base and a strong base. But in this one, where you're doing elimination, we use concentrated strong base. But in this one, we use a dilute strong base. And if you are going from a haloalkane to an alcohol, that is just a substitution reaction. If you think about what we... Oh no, that was a previous thing. If you think about the way it works, if you have a haloalkane, okay, let me just draw a random haloalkane. So something like, let's say, I'm just making up a random one, okay? It's not the one we have in our example, yeah? And you react that, for example, with NaOH, but not a concentrated. You have to use a dilute. Otherwise, if you use concentrated, it will do elimination like we saw in the first part of this question. Then all that happens is that this OH is literally just going to switch places with the Br. So they're just going to switch places, okay? You're not going to form a double bond. We're not eliminating. We're just substituting. So you would end up with something like that over there, and then you would be left with NaBr. That's just an example, but can you see that we literally just switch these two things out? So it says write down the type of reaction that takes place, substitution. You can also call it hydrolysis. We can also call it hydrolysis. Okay, that's not a very common way of calling it, but it is correct. Now it says besides heat, write down the other reaction condition needed. Well, this is where you would say use a dilute strong base. You must use the word dilute. You could say dilute NaOH. You could say dilute KOH. But you could also just say dilute strong base.